Good afternoon or good morning, depending on where you are. My name is Professor Duke Orata. We are continuing with our lecture series in thermodynamics. Today we want to look at what we call the indicated mean effective pressure and what it wants to bring us to. We have done calculations and looked at several work cycles in machines. And one of the things we want to do today is to be able to do it empirically. How do we actually determine these indicator diagrams? You know, indicator diagrams tells you about the work done. Because remember, we are talking about the pressure volume axis, and so if you have pressure, which is force per unit area, that product with the volume, which is area times displacement, you have force times displacement, which leaves you with work. And so these are very, very important quantities. Let us first of all look at a mechanical indicator. A mechanical indicator which we can attach to a machine system and be able to generate some graphical representation of the work done by the system. So let's work with the real PV systems. So, in this mechanical indicator, let's first of all have a schematic representation of what we are talking about. We have this low rotational machine, and we have this mechanical indicator which will track its movement, and that movement is in relation to the engine piston stroke. And so we are going to have this mechanical indicator which will be attached, which will be interfaced with this drum, rotating drum. There will be a stylus from it which will be making some marks on the chart paper on that rotating drum. Now, what kind of a system are we talking about for this mechanical indicator? Remember, when you're talking of indicator, it comes from the indicator diagrams, which we saw for pressure volume work that we've gotten, for example, that isotherm, and for a reversible pressure volume work, we had that. This is an isotherm, and we are seeing that depending on so we have pressure, volume, so if V1, V2, for example, expansion, and irreversible conditions, that one, let's just do it properly a bit. The work was given by the area under that curve. And what I was talking about is, when you look at the pressure volume axis, pressure is force over area. And volume is area times displacement. So that these two areas cancel, you're left with force times displacement, and that gives you work. Now, so the area shaded under this curve here gives you the work. For the reversible process, it will include all that. But when we have an adiabatic process, which falls under polytropic processes, then you will have this case where P is inversely proportional to V gamma. Here P is inversely proportional 1 over V. Remember, for polytropic processes, we say that PV gamma, PV raised to power n, was a constant. And that was the polytropic. That's the polytropic index, or expansion compression index. So we just reminded ourselves. So what we are saying is this: can we have a practical system which can generate this kind of a graph? That's the indicator graph. And that's what the mechanical indicator is going to do for us. That's what the mechanical indicator is going to do for us. So first of all, what is this mechanical indicator? This mechanical indicator is attached to a low rotational machine, and that unit is a simple piston cylinder unit. It's a simple piston cylinder unit. So what's a piston cylinder unit? Remember, we had our system. Let's just remind ourselves. The piston cylinder unit. We have our system. Remember we talked of valves, inlet valve or an outlet valve. Then remember we had our sparking system or fuel injector. And we have our piston. Remember we have our piston. These are of course the oil and compression rings. And we have our piston here. We have our cylinder wall. And remember this piston is connected to a rod. The rod. This is a rod. Here we have rotary motion. And this is a reciprocating motion. And we say that, let's say that we have that as the bottom dead center. And let us say that we have this as the top dead center. So, between these two configurations, this represents the stroke, the piston stroke. And here we have the clearance volume. And we say this clearance volume is very important. If this piston is not to collide with the cylinder head, if that piston is not to collide with the cylinder head, then that clearance volume is necessary. And of course, the operation of the valves also has to be cleared. They have the valve clearance has to be in good, must be as per specifications for that particular engine. So very important for us to remember. So we have remembered basically what we have. So what we are saying is this: how do we generate this indicator diagram empirically, that is in reality, in practical terms? Now, so what we have in this particular case is we are going to have a very simple piston cylinder system attached to this low rotational machine. And it's very simple in the sense that in the first place, its volume should be less than the clearance volume. It's a simple unit. And it's attached to this low rotational machine. And this piston itself is attached to a spring that ensures that the movement of the stylus, which will be drawing the profile on the chart in the drum, is proportional to the pressure. It's proportional to the pressure. Let's just have a schematic of it. So let's just have a schematic of it. So let's say we have here our piston. And let's say that's the rod. We have the piston rod somewhere there. So we have a spring. And this spring constant will be very, very important in terms of what we do. It will be calibrated so that it corresponds to the pressure readings, pressure units. Now, the spring constant, so we have the piston. And let's say that it's mounted on something. We've mounted it on something. There's all manner of we have mounted it on some mechanical support unit. And so with this piston, we have a stylus interface to it. Think of a stylus in a simple term, layman's term, as a pen, which is able to draw something. And so we have this, our drum. Let's call this a drum. Our chart paper. Our chart paper there. So it's able to draw something. Now, in reality, what kind of profile will you get? What kind of profile will you get when you're done with your mechanical indicator? I repeat, very simple. This is a simple piston cylinder unit where the volume of that unit is less than the clearance volume. Point number 2, we are saying it is attached to a spring. so that whatever movement of this stylus here, whatever the movement of this stylus here is proportional to the pressure, is proportional to the pressure. And we have this drum which is rotating, and we have the stylus which is making those particular markings on the chart paper. Now, what kind of thing are we talking about here? What is the picture which we get? So if we have our unit, pressure volume, cylinder pressure, cylinder volume, let's have our system here. So let's say that's our chart. And so we are talking from, we have, let's say V2, V1, this is a compression, this is power, and we are having, let's just draw the profile of a cylinder, this particular point of the bottom dead center, so that corresponds to the top dead center. This is the clearance volume. Now, whatever figure we get which is normally rectangular will be corresponding to the area under this PV profile. So that what we have that rectangle there, let's say that's its length, that rectangle there, that is its length. And so this quantity here, call it P2, call it P1, let's erase this so that we get clearly what we want here. This still, let's just call this cylinder pressure, P. So this represents the mean pressure. And that mean pressure simply corresponds to that length corresponding to this particular rectangle, So I'm just saying that these points correspond to this. They're not part of the rectangle. I'm just indicating that they correspond to those 2 points, that particular point. So it corresponds to that particular length of that rectangle. So that basically, if you know the area, of that rectangle divided by length, it should give you that height. That height corresponds to the indicated mean effective pressure. Now, and of course, we say this corresponds to the stroke, engine piston stroke. So let's not forget that. Now that we have seen what that is, we know that in general, the expression for work, is dW is equals to the integral of P dV. And so for our system here, I repeat, we have just this piston cylinder model, very simple piston cylinder unit, whose volume is actually less than the clearance volume. It's attached to a low rotational machine, and it is also interfaced with the stylus, which can draw on the chart on that rotating drum. And so the profile which you get, that area, that figure which it draws, is basically the same as the area of the actual indicator diagram for the process. So that the value which you get, that is that height there. That height there corresponds to the mean pressure. That's the indicated mean pressure, the effective pressure. So what does that mean? That effective pressure, if it acts on that piston whose surface area is A, and it covers the piston, the engine piston stroke, then that will correspond basically to the work done by that particular machine. Now, so we are talking of in terms of to compute work. So we are saying that is from P2. So we have that as P2 minus P1 dV. So we are starting from 0 to L. That corresponds to that stroke there. So what we are saying is that this, is basically integral from 0 to L, P2 minus P1. That, remember, is the indicated mean effective pressure, and this is A dL. Of course, A here, A is the area of the piston, and L corresponds to the engine piston stroke. And so this expression here will give us the expression for work, for the effective, for the work done by the system. But remember that the indicated mean effective pressure is simply that length. Let's call it L1. Let's call it it corresponds to that L1, which is P2 minus P1. So it's P2 minus, so it corresponds to L1, which is basically what we have marked here as P2 minus P1. And of course, this is work, because what we have here is simply P2 minus P1, A times that is, remember, that is volume. So pressure times volume, like I've always said, that is the work done in that particular process. So that effective, that indicated mean effective pressure is corresponding to the work done by that machine. If that PIM, that's the effective pressure, was acting on that piston whose area is A in terms of surface area, and through that distance corresponding to the stroke in that particular piston, So that's very important for us. What we have learned is that we are able to actually empirically determine the indicator diagrams associated with a work process. So it's not just theoretical. It is actually can be computed empirically. In other words, you can do measurements, and you can do measurements using that mechanical indicator like we have shown, and you're able to interpret the information which you get, which will give you actually the work done by that particular machine. And of course, the rate of work done will depend on the revolutions per unit time, or number of cycles per unit time. So the rate of work done, that you just multiply, rate of work done, let's just call it rate of work done here, will simply be whatever we have, that is and AL times, multiply that, remember that's the engine stroke, piston stroke, now multiplied by some N, where this N is revolutions per unit time. If revolutions make you a bit nervous, just call it the number of cycles per unit time. And we have used that in our earlier discussions on work cycles in machines. So just look at the lectures which we have talked about heat, we have talked about work, mass flow rates, you'll see that we have used that number of cycles per unit time with the rate of work down. So let's stop at that. We are continuing with our thermodynamic lectures.